Good morning. Today we are going to continue with looking at the application of the force method for analyzing statically indeterminate structures. Last time, if you remember, I had said that today we are going to consider flexible supports and see how that can be included in the force method procedure to be able to analyze a structure. Okay. So, let us look at what we have, and so this is the same truss that we had considered last time, excepting that the roller here has been replaced by a flexible spring support, where the flexible support, the flexibility is given as 1 over EA, where EA is the value that we have for all the members, axial rigidity for all the members. All of them are EA. If you remember, that is what we had considered last time. And this, I mean, you see, I am just taking a flexibility value, I am taking it to be 1 upon EA. It is not necessary that this has to be 1 upon EA, it can be any flexibility that I define for this spring. Okay. I am just, in this particular case, I am defining as 1 upon EA because I am going to solve it using 1 upon EA. However, you can use any value of f and you will see that it's whatever procedure I develop will be equally valid for that procedure. How do we solve this problem? Okay. The last time we saw how to get the support reactions, including by what did we do? We took one of the, by the way, this is a single degree of static indeterminacy problem. This is the same problem as we dealt with last time, so I am not going to go into all those details again. Okay. This time I am just trying to see how we can consider the effect of additional flexibility in the supports. Okay. And I have considered this support to be flexible. When would a support be flexible? In real life, when would this happen? This would happen in case you had a pier where you considered the axial deformation of the pier. Because if you considered the axial deformation of the pier, then you see the pier becomes actually flexible, and since the pier is essentially subjected to vertical axial forces, because that is how the load is transferred through the pier, what happens is essentially that we are now considering the pier to be actually deformable, and what we are saying in this particular case is that the pier flexibility is given as 1 upon EA. That is all that we are saying in this particular case. Okay. So, anyway, how do we solve this problem? Again, basically the problem goes in the same procedure as last time. You have to develop your statically determinate base structure. I am going to have exactly the same thing as last time. I am cutting this member so that I get a statically determinate structure. Okay. Then I need to continue having this, and these are the loads. Okay. So, this is my base structure, and this plus this plus this is equal to this. So, in essence, there is no difference in the solution procedure just because you have a flexibility. Okay. What you have in this particular case is the following, that if I look at the base structure, This is my base statically determinate structure. If I have a statically determinate structure, and remember that this is, I am taking exactly the same thing as last time. Okay. So, the first step in analyzing this structure is what? Is to find out the reactions okay. And as we see last time, the reactions are identical. This is going to be 10 and 10, and then due to this 30 by 4. So, this is going to have a 17.5 kilonewtons, 2.5 kilonewtons, and this is going to be 10 kilonewtons. If you look at this, this is identical to, so therefore, till now we have not considered any aspect of this flexibility. Okay, we have not included this flexibility into the entire system. However, the most important point here is that whereas in the previous case this deflection was 0 because it was a roller support, in this particular case there is going to be a deflection. Okay. But the overall point is that this deflection does not affect the forces in the structure at all. What it may do is, it may affect the displacements in the structure. So, therefore, the whole point is that even if I solve this structure, okay, if I solve this structure and I were to find out what the value of x1 would be, okay, you would see that as far as the forces in the members are concerned, whether I have a flexible support here or not will not matter at all. So, therefore, in this particular problem, I am going to try to evaluate something else. I am going to, remember I said last time that, well, we could find out this displacement in addition to finding out all the forces in all the members. Okay. So, now if I do that, then you see it is not just a question of finding out the forces in the members and the deformation in the members. I also need to find out what this displacement is going to be due to these forces. Now, how would I do that? Okay. Remember, to find out the forces, the displacement at this point due to all these forces, what I need to do is, I need to find out, I need to apply a force there. Okay. So, therefore, you see now under this system, I am trying to find out two things. Okay. I am trying to find out the separation at this point, and I am trying to find out the displacement at this point. Both of these are things that I need to find out together. Okay. And I have the flexible support. Okay. So, how do I do this? Well, in terms of this particular structure, okay, all I need to do is I need to find out the forces, and going back to the previous, I don't want to go back and do the same thing all over again. So, I am going to just put the previous structure that we had done, and if you look at this, these are the forces in all the members. Okay. These are all the forces in all the members, and if you look at it, so these are all the forces in all the members, and what we need to do now is find out what the forces due to the two. Now, you see, what am I finding out? I am trying to find out the separation at this point, and I am also trying to find out the displacement at this point. So, to do that, one is to apply a unit force here and find out, that is the unit virtual force, so that I can find out what the displacement at this point is in the original structure. Sorry, in the statically determinate structure, this displacement. Okay, so I am applying a unit force, and this is identical to what we had solved over here. If I put x1 equal to 1, then FAB is equal to 3 by 5, 4 by 5, 1, 3 by 5, 4 by 5 and 1. We've already looked at all of these last time. So therefore, there is no need to solve this particular problem. It's identical. So to find out the other displacement, what do I need to do? Note that again, in this particular case, what I am doing is, to find out this displacement, I need to apply a force at this point. Okay? And now let's look at what happens. This is my flexible support. As far as the forces are concerned, let's see what happens here. If I apply a unit force here, then the reactions, this is going to be 1, and if you look at these reactions are going to be equal to 0. What does that mean? That means that due to this displacement, all that we have is we have a unit force in this, and all others are 0. Okay. So this gives me, this is the virtual force that I am applying here, and I am finding out the virtual forces in all the members and the virtual support reactions that we have. Okay. So now the point that I am trying to make over here is that you just need to go through the same step procedures to get your this displacement. What do you do? Well, there are two steps. One is, let me write down, this is delta L. How do you find out delta L? Delta L is due to the load alone, which is due to this. Okay? How do you find out that delta L? We've already gone through the steps last time, so I'm not going to go back and do the same thing. Okay, you can find out this deflection and this deflection in this structure by just writing down the virtual work equations, where the deformations, the real deformations at this point are actually applied, the real deformations are multiplied by the virtual forces developed due to this and this. Okay, so understand that this delta L that I am finding out is what? This is the separation of member BD due to loading in base structure. So this is the separation of the member BT due to loading in the base structure. This, how do I find this out? Well, I'd find out the forces in all the members due to this, the virtual forces, and multiply them with the real deformations due to the loading. We've already got this earlier. There's no difference in this particular case. The next thing that I'm going to find out is R1 due to L. That is the horizontal displacement due to loading in base structure. So therefore, how do I find this out? Well, I find out the deformations in the member and then find out the forces and all the virtual forces in all the members. So if you look at it, what really happens? You will have R1 in the real structure, that's R1L into 1, that is the work done by the external forces, is equal to 1, that is member AD, 1 into the deformation of this member delta AD in the original structure. That is due to these loading. We've already found those out earlier. If you look at it, this, so the delta in this, what is this delta? If you look at this delta is equal to 0. So if it is equal to 0, then what is the delta in this? 0. So what is the deflection at this point due to the loading that we have? 0. Okay, so you can find that out. Okay, this is very easy to find out. So this I have found out in the base structure due to the loading. Now what's the next step? I also need to find out the delta x. What is delta x? Separation of member BD due to x1. This also I can find out, because what is the real structure? The real structure is the one with x1 applied here. Find out all the displacements and deformations, forces in the members and the deformation in all the members, and then take this as the virtual force, and I can find out this delta x. I have already found this out last time also. If you remember, the delta L that I got last time was this. The delta x that I got last time was this. Okay, so there is another aspect that I need to consider, and that is R1 due to x. That is the horizontal displacement due to x1. How do I find that out? Well, in that case, my real structure is this structure. So I can find out the forces and the real deformations in all the members, and my virtual structure is this structure. Okay, so I can find out the virtual forces which I have found out, and then I can do the virtual work to get Rix. Okay, so therefore, what is the final solution? The final solution you will see is delta, that is the deformation, the separation in the original structure is going to be equal to delta L plus delta X, which by the way is equal to 0 because there is no separation, and R1 is equal to R1L plus Rix. Okay, R1X. Note that this gives me, like last time, I found out that x1 is equal to minus 25 by 3 kilonewtons. There is no difference in the flexibility at all. Okay, and once I find out x1, I can find out R1x, because R1x will always be in terms of x1, and since I know x1, I can find this out, add it to this one which is a number, okay, and I've got my displacement at this point. Now you may ask, in this particular case, how does having the flexible support affect this entire process? Well, it actually does not affect this at all. It does not affect this at all. Okay, does this affect this one? Well, you will see, I'm not going to go into the details, you can actually solve it yourself. You will see that this one is not going to give anything, primarily because if you look at this problem which we solved, the primarily problem is that since this is equal to 0, this is equal to 0, you see R1L turns out to be 0. Okay, and since R1L turns out to be 0, R1 is only due to R1X, okay, and that is not affected by the flexible support. So you may well ask that what does the flexible support do for this particular problem? Well, actually, all the things that we have found out, it does not affect. The flexible support does not affect. What would the flexible support affect? Well, it would affect, for example, if you were to find out this displacement. I leave this as an exercise to you. Find out the displacement in this structure, this displacement, okay, due to these loads, considering two situations. One, where you have the roller support. Okay, so do you understand the problem? I want you to find out the deflection at this point in this statically indeterminate structure due to this loading, where this is 4 meters, 3 meters. All of these members have a flexural rigidity of EA, and I also want you to find out this displacement due to the same set of loads, excepting that the roller support is replaced by a spring whose flexibility constant is 1 upon EA, okay, where EA is the flexibility of all the members. Find these displacement out. I am giving this as an exercise to you so that you can actually apply the principles that we have been talking about. Find out the displacement at this point due to these loads. Okay, so this is your first problem, problem A, and then find out this displacement, which is problem B, due to this. I am going to tell you right up front that in this particular case you will see that this displacement and this displacement are two different values. That means that the flexibility of this support has an effect on it. Okay? So therefore, there are certain responses that are affected by the flexible support. There are other responses that are not affected by the flexible support. I just gave you two examples where the flexibility of the support does not affect the response. However, I have also given you one exercise where you will see that the flexibility of the support does have an effect on the displacement quantity that I am trying to find out. Okay. So, where do we go from here? Well, simple. What we have to do is we have to find out what other effects that you can have in a structure, okay, which may affect the static analysis, the analysis of the structure. Let me look at another classical situation. I am going to remain with trusses for this particular lecture, because I want to look at all the effects that you may have to consider in addition to the effect of the static indeterminacy. Okay. So, let us look at what kind of a situation. Let us look at what I call as lack of fit. What is lack of fit? Well, let us say that this is the same structure and now I am going to go back to the roller support, and I have these loads. A, B, C, D. Okay. So, this is exactly the same structure. Okay. This is 4 meters, this is 3 meters. So, member AB is 3 meters, member CD is 3 meters, member AD is 4 meters, member BC is 4 meters, and member AC and BD are 5 meters each. Okay. 3, 4, 5 triangle. Okay. So, these are the actual lengths. So, let me write it down. Length of AB is equal to length of CD is equal to 3 meters. Length of AD is equal to length of BC is equal to 4 meters. Length of AC is equal to length of BD is equal to 5 meters. This is the geometry that I have. So when I give this geometry to someone, what are we saying? That please make the length of AB 3 meters, length of CD 3 meters, length of AD 4 meters, BC 4 meters, AC and BD 5 meters. This is what we have given. However, you see, whenever you are putting together members, how do you do? What you do is you never have a member of size 3 meters exactly, right? What you have is probably 2 members of 10 meters each. So what you have to do is you have to cut them up so that you get exactly the sizes that you have. Okay. There's also the factor that what we call as 10 meter length may not be exactly 10 meter length. So therefore, there is this aspect that even though we want AB and CD to be 3 meters, AD and BC to be 4 meters, and AC and BD to be exactly 5 meters, in reality, when someone actually cuts the members and puts them, you might have a situation where some members are not exactly the size that they are supposed to be. In this particular case, let me take the situation that let's say that LAC, when we cut it, actually turns out to be 5.005 meters instead of 5 meters. That means, what does that mean? That essentially means is that there is a plus 5 millimeter lack of fit in member AC. In other words, member AC is actually 5 millimeters longer than it's supposed to be. What effect does that have on the structure? If it was a statically determinate structure, it would have no effect on the forces in the members. All that would happen is that the structure would no longer be exactly a 3, 4, 5 kind of triangle. There would be some small displacements, the nodes would be shifted slightly. However, there would be no additional forces in the members due to the lack of fit alone. Okay. However, in a statically indeterminate truss, that is not true. I am now going to show you that due to this lack of fit, there are going to be additional forces in the members. And to do that, what I am going to do is, I am going to forget about the fact that you have a loading on the structure. You see, what I am doing is, I am taking the problem as 2 parts. One part is I am finding out the forces in all the members due to the loading alone. That I have already done last time. I am not going to do that, repeat that here. What I am going to do is, what is the additional effect of this lack of fit that I have because of the fact that member AC is 5 millimeter longer. That is the only problem that I am going to be solving here right now. Okay. So let's see. So therefore, we have this situation that member AC is longer. What's going to happen? Okay. So you have this structure. No loading on it, no loading at all. The only thing is that this is A, B, C, D. The only thing that we are trying to find out over here is that actually AC has a positive lack of fit. Okay. In other words, what we have is that member AC, okay, is 5 millimeters longer than it should be. Okay. Now I can look at this problem in this manner, that in the base structure. So I am going to still solve this problem as two problems. Okay, it's still two problems. Okay, plus, only thing note is that there is no loading. There is no loading. Okay, and the second problem is okay. So this is all. This is the same problem, excepting note that in this structure, if you look at this, okay, there are no forces in any member. Okay, but I can say, and this is how you solve a lack of fit problem. I can say that look, in this particular structure, delta AC, that is, I can say that the lack of fit turns out to be a deformation in member AC. Do you understand what I am saying? I am saying that in this structure, which is the base structure, okay, none of the members have any forces in them, none. However, the lack of fit essentially means I am treating this problem that actually, due to some reason, delta AC, the AC which is supposed to be 5 meters, is actually 5 millimeters longer. Okay, so I am calling that well, this is the structure, this is the original structure, and I am saying that well, this structure, this member AC is longer by 5 millimeters. So I can take that longer as a deformation in the real structure. Okay, so this is the deformation. Now what I need to do is, what is the effect of this deformation? Okay, note that I still have this 3, 4, 5. Okay, and this cut that I made was in the 3, 4, 5 triangle. Now suddenly AC is longer. So what's going to happen actually, this point cannot go anywhere, and to ensure that this is longer, this will have to move somewhere along this direction. Okay, so then it will move 5 millimeter in this direction, okay, longer, and because of that there is going to be a separation at this point induced due to this. So I need to find out what the separation over here is. How do I find that out? Well, again, use virtual displacement. So if I use virtual displacement, what do I have? Well, let's go back to apply a unit virtual force here, and I have already solved this particular problem. Okay, and what did we get? We got this. So I am going to just put that down. I am just going to copy that down without actually doing the analysis. So this is 4 by 5. This is 3 by 5. This is 4 by 5. All the support reactions are 0. 3 by 5, okay, and 1. So these are the virtual forces set up due to applying this. So now this one, what do I have to do? Well, I am going to use virtual work principle. So I am going to say that external virtual work is equal to internal virtual work. What is the external virtual work? Delta L. Now note that this delta L that I am writing down is not due to loading, so I will call it delta 0. You know, it's the separation at this point due to the base structure. So delta 0, that's the real displacement, multiplied by the virtual force, that gives me the external virtual work, is equal to the work done by all the real deformations. What are the real deformations? AB 0, BC 0, CD 0, AD 0, okay, BD obviously 0, okay, and AC plus 5 millimeters. So if you see that what I have to do is all of them, all these forces, virtual forces, are multiplied by their corresponding real deformations. All deformations are 0 excepting for in member AC. So what I have to do is, what is the member AC? Plus 5 millimeter, okay, which I can say, if I want to put it into units of meters, is 5 into 10 to the power of 3 multiplied by, what is the force, virtual force in the member? 1. Okay, so this gives me that what is the separation in the real structure due to? It is plus 5 into 10 to the power of 3 meters or plus 5 millimeters. What does that mean? Because of this being longer, what has happened is that this has overlapped. Okay, great. So we've computed that. So I've computed the delta 0. Now I need to compute what? I need to compute the delta due to x1. Okay, now that I already have done last time. So I'm going to just take that down. Due to x1, I need to find out the displacement at this point. This I have already done last time. If you remember, I had already done it, and that delta x turned out to be 5 upon EA into x1. Okay, this was what? This was due to, these were all due to the internal force. Okay, so what did I have? I had the situation where, just 1 second, I'll compute that for you. The delta x was equal to 432 upon 25. This still remains the same. So therefore, the delta x is equal to 432 upon 25 EA into x1. So this, therefore, what is the total delta? Total delta is equal to delta 0 plus delta x equal to 0, which implies that 432 upon 25 EA x1 plus 5 millimeter is equal to 0. From that I can find out x1 value. Okay, depending on what the value of E1 is, I will get. The main point to note is that x1 is not equal to 0. So do you understand? And once x1 is not equal to 0, all the member forces will depend on x1, because if you look at it, given x1, all the forces in all the members can be found out. So understand this. I had this situation where I didn't have any load. Only thing that happened was that AC was 5 millimeter longer than it should be. And because of that, you have forces in all the members. Okay? So therefore, a lack of fit actually gives rise to additional forces in the members in a statically indeterminate structure. Okay. So what have we considered till now? We've considered how to find out forces in a truss due to loading. We've done that. We've found out the effect of the flexibility of a support on the truss. We saw that the flexibility of a support does not directly have any effect on the forces in the members. However, it can affect some of the displacement quantities. Okay. And third thing that we looked at was lack of fit. What effect does lack of fit have on a member? Okay. And we saw by an illustrative example that a lack of fit in a statically indeterminate truss, which is not subjected to any load whatsoever, gives rise to member forces. Okay. And we have found out, using the virtual work principle, the method of virtual force, we have found out how to get that particular values of all the forces due to a given lack of fit. Now remember, you see, since we are dealing, I want to establish this once and for all. Since we are dealing with linear structures, okay, any effect on the structure can be considered separately, and since the method of superposition is valid for linear structures, you can just find out everything due to one effect and then everything due to another effect, and just keep adding it up, and the sum total of all the effects is just going to be solving the problem for each individual effect and then adding up to get the final effect. So therefore, even if I had this situation where I had this case, you see this case where I have a loading, in addition to that I have a lack of fit. I can solve this problem in two ways. I can say, well, forget the lack of fit. I'm going to first consider the effect of the loads, find out all the member forces due to the loads alone. Then I'm going to forget about the loads completely, and I'm going to take only the lack of fit. I'm going to find out all the member forces due to the lack of fit alone. And then what if I have a situation where all the loads and the lack of fit are there together? So therefore, if I have a structure where I have all the loads as well as a lack of fit, I can treat this problem as a superposition of two problems. One problem where there is no lack of fit. The member AC is 5 meters and we consider the effect of the loads. Analyze the structure for that. Okay. Then I can solve another problem where there are no loads, there is only the lack of fit. Solve that problem. Okay. And then superpose the effect of the loads and the effect of the lack of fit onto each other. In other words, I add up all the analysis results that I get for the load alone to all the analysis results that I get for the lack of fit alone. Add the two up, okay, and I've got the effect due to both the loading and the lack of fit together. Okay. So this principle of superposition is valid, and therefore you will see I will put situations where I consider only one effect. The reason behind that is that, well, if I consider each effect separately and add up all of them, I'm going to get the combined effect anyway. Okay. This is of course true only for linear structures. In this course we are only looking at linear structures, and therefore we can use the principle of superposition. Okay. So coming back to where I was, I have considered loading, the case of loading alone, how to find out the response of a statically indeterminate truss for loading alone, we have done that. For flexible support, we have done that. For lack of fit, we have done that. Now we have to consider another aspect. If we consider that aspect, we will have considered all the cases that could possibly arise in a truss. Okay? And that is called as thermal stresses. What are thermal stresses? Thermal stresses are forces developed in the structure due to a temperature variation in the structure. You see, what happens essentially is that let's take the situation that I put together this structure. There is no loading, I am constructing. Okay? All the members are perfect. In other words, in this particular case, member AB and CD are all 3 meters, AC and BD are 5 meters, BC and AD are 4 meters. Perfect. We've all put it together. We've constructed this truss. We've prepared the supports and put the truss up. Okay. Now, when we built this truss during the night when the temperature was 10 degrees centigrade. Okay. Now, we put the truss up and in the middle of the day, the temperature is 30 degrees. What effect is this going to have? First of all, there is this aspect, these are ambient temperatures. Okay? There is this entire concept on how ambient temperatures actually give rise to temperature distributions in the structure. I am not going to go into how to treat ambient temperatures and go to obtaining in the members what are the actual temperature variations that the members are subjected to. So, in this case, all I am going to do is I am going to consider that, well, due to whatever ambient temperature, okay, member AC, okay, let's say that member BD is thermally insulated. What does thermally insulated mean? That no temperature change has any effect on member AB. Member BC is also thermally insulated. Member AB is thermally insulated. Member CD is thermally insulated. Member AD is thermally insulated. Unfortunately, member AC is not thermally insulated and it is seeing this additional 20 degrees change. What happens? That means that the delta T for member AC is plus 20 degrees. Okay. What happens in this case? Okay. Think of what happens when a member is subjected to an increased temperature. What happens? The member elongates, right? How much does it elongate by? Well, that is given by the coefficient of thermal expansion. What is the coefficient of thermal expansion? Coefficient of thermal expansion is alpha. Okay. So, alpha is the strain that the member is subjected to due to a 1 degree rise in the temperature. Okay. So, alpha is the strain in the member due to 1 degree rise in temperature, additional strain, axial strain. So, this into the total temperature rise will give me what? Will give me the strain in member AC. And if strain in member AC, what is the deformation of member AC? It's strain into L. In other words, delta AC is alpha delta AC L AC. Okay. So, what does thermal stress do? Thermal stress leads to an elongation, a real elongation of the structure. Okay. How will I solve this problem? Well, do you see any difference between this and the lack of fit? None. Again, the real deformation in the member due to thermal stresses gives rise to delta AC, which I can compute given alpha, delta AC and LAC. And once I have this problem, you can treat this problem exactly as we have done the lack of fit problem. Okay. And that in essence is your analysis of a truss for flexible support, lack of fit, as well as thermal stresses. Thank you.